dynamic epistemic logic we know as some theory of change of knowledge interpreted on Kripke models, where Kripke models are abstract objects, you might say relational structures with a set of things and some relations between these things that describe indistinguishability and some facts that are true and false in these points, and then you can do change of these structures, and that's dynamic epistemic logic. We will see an example. Combinatorial topology is something completely different, at least for me, up to recently completely different, which is used mainly in distributed computing to model concurrency and asynchrony. And here the basic structure is not, well, it's still you might say a set of things where you do the things with those things, but here the simplicial complex is the basic structure. So we have a set of vertices and you have a set of subsets called simplices of that set of vertices closed under a subset relation, under containment, and then you can start doing all kinds of geometric manipulations, including in some purely combinatorial way, and that models quite a number of dynamic phenomena in distributed computing, equality negation, immediate snapshot, and so on. So to start with an example of an epistemic model and a simplicial complex, let us have two agents, M and Bill. M knows the truth about P, Bill knows the truth about Q, and then there is an environment that informs these two agents about that P or Q is true. So this initial uncertainty we model in this Kripke model on the left-hand side, where the names of the states are in red, the names of the agents are in blue, and the names of the propositional variables P and Q are in black. So here we have, for example, that here P is false and Q is true, and here P and Q are both false. So A cannot distinguish between these two states, but that means that A knows that P is false because P is false here and there. Here A knows that P is true, here B knows that Q is true, here B knows that Q is false. And so A knows the truth about P and B knows the truth about Q. Then after the public announcement with P or Q, we have this restriction of the model where in this particular state where P is true and Q is false, agent B now knows that P is true. And so B has learned something. There's no longer an alternative where P is false. Exactly the same model can be represented as a simplicial complex, where we have some kind of duality almost, at least in this setting, because there are two agents, where miraculously here we have that the nodes now are labeled with the agents, whereas the edges are labeled with the states, and well, and the propositions are still there where they were before, but now separated over the agents. And there's a typo of course, because this should be a Q and not a P. So what does this say? Well, there's a state for agent A, characterized by P being false. And there's a state for agent B where Q is true, and here for B where actually Q is false, not P is false. And this now means that A is uncertain between, well, B having Q true or B having Q false. So we separate the information in these nodes over these two nodes where there is now one per agent, whereas in the Kripke model, a state represents the uncertainty for all agents, and then the duality between these two structures is complete. You can do this in both directions, and we can again process the information that P or Q is true, and we again get some kind of model restriction, but now it's a restriction of a simplicial complex. Similarly, you can have other information, for example, more typical distributed computing style, where agent A informs agent B on the truth about P, and that removes the uncertainty for agent B in any state of the system. So we have now two disjoint models wherein only A is uncertain, but B has learned everything. And this can again be represented as a transformation of a simplicial complex into well, another simplicial complex that consists of two disjoint parts. What are these simplicial complexes? Well, as said, it is based on an abstract set of vertices. We determine a set of non-empty finite subsets of this set of vertices. These subsets are called simplices or simplexes. And it should contain all the singletons, all the vertices themselves. And if such a structure has the property that all the maximal simplexes, the simplexes of a maximal number of elements have the same dimension, we call it pure, and otherwise it's impure. The distinction will become important later. Now, the particular simplicial complexes that we investigate in this setting, then these vertices are not even well, abstract things, but they are, you might say, linked to individual agents. In combinatorial topology, these agents are called colors, but I simply call them agents here. And it is then required that all vertices of a simplex must have different colors. Also, just as in Colloquium models, in these points, in these vertices, you can determine whether a fact is true or false. But this now means that this fact is local for the agent that colors that vertex. Let us see a two-dimensional simplicial complex for three agents. So the dimension is actually one less than the number of agents. Here we have another Colloquium model, one that is not uncommonly seen in some of my works, that represents that three players have uncertainty over who holds which card. So we have a stack of three cards, everybody draws one card, so you know only your own card. This is your local state. So, for example, given that the cards are 0, 1, 2, the deal of cards could be that A holds card 0, B card 1 and C card 2, and this is indistinguishable from the deal of cards where the cards of B and C are swapped, where B holds 2 and C holds 1. So therefore there's a link labeled with A between these two states. Now, what does this single state for three agents become in a simplicial complex? Well, it becomes a triangle. It becomes this triangle. It's the same red S. In this triangle, we separate out the agent, so to speak, over what agent B knows, namely that he holds card 1, over what agent A knows, namely that she holds card 0, and what agent C knows, that she holds card 2. And indistinguishability between two different distributions of cards now means that these triangles intersect in one vertex, in one point, that is the point for agent A. So agent A doesn't know whether this is the case or whether that is the case. Similarly, agent C, who holds card 2, is uncertain between the distribution 0, 1, 2, or the other distribution 1, 0, 2, wherein the cards of A and B are swapped. Similarly, agent B, and so on. Now, well, what's the nice thing about geometry? Great pictures in TICS, in LaTeX, but sometimes you need even more than 2 dimensions, but 3 dimensions, and we can't really get this right here. So actually, you have to identify this node where one holds B with this node, and this node where this node, and this node with this node. So this flips over, but this is becoming hard to, well, it's becoming harder to visualize. Okay, given this structure, these have complete duality, and we can then evaluate things about knowledge or things about the dual aspect of knowledge in either structure. So just to give an example, in this state S, the point of evaluation for the information, we can, for example, model check that A knows that she holds card 0 because in all states that she considers possible, it is the case that she holds card 0. Well, this sounds self-evident, but we can also determine, for example, that the head means consider possible, that A considers possible, that B considers possible, that C holds card 0, because we can make a path for A going from here to here, and then for B to here, and in that way you can model check that this proposition is also true, and so on. Now, going back to dynamics, as an example of dynamics in logic of knowledge, we saw the public announcement. An example of dynamics in distributed computing is, for example, the immediate snapshot. You have some kind of distributed system where the agents can interact with each other by sending or receiving messages, and you want some well, snapshot indeed in English, some sort of more or less point in time to be precise about what the agents all know at this stage. It's some kind of synchronization of an asynchronous system at some sort of round of events that closes off a certain moment. So there are a number of ways to model this, but in what is known as the immediate snapshot, the agents communicate with each other by way of a shared memory. And the idea is that they all, well, more or less simultaneously, but not exactly simultaneously, write their value on this memory and then read all the values that have that are available on the memory on the shared memory at that stage. Now, what may happen is that, for example, A does this slightly before B, and B does this slightly before C. Then we have in this A.B.C situation that A, well, writes A and reads only A because that's the only thing available. Then B writes B but reads A and B because A has already written her information. Then C writes C but reads all three informations. And from the perspective of C, this is not very different from a different schedule or communication pattern, wherein A first, well, does the write read thing, and then B and C do the write read thing together, because C will still read all values, only for B it's different, because here B reads A and B, whereas in the A.BC, B will already read A, B, and C together. So there are a number of different ways in which these agents, well, almost at the same time do their read-write thing together, and this can also be modeled in combinatorial geometry by a very elegant thing that is called a chromatic subdivision. And the relation with dynamic epistemic logic is that one can also do this in in a setting that is purely about knowledge and change of knowledge, and that has nothing geometric, although it has a lot of combinatorial aspects. So what is this chromatic subdivision? Well, here we have three agents in some particular state of the system, and here we have a subdivision, and indeed it still looks kind of topological, right? It has the same shape, but now we have lots more triangles. If you want to interpret this, so the action in itself means that all the agents, well, drop that information and then get the information of the others in case available. Now, the triangle in the middle means that this has really happened for all three at the same time, so they have all the information of all the others. But it could also be that, for example, A got there first, and then B and C second together. This was this other option, and then we are in this triangle. And in this particular triangle, at the bottom here, it means that A got first, and then B got second, and then C got third. So there is a way to interpret this also in terms of knowledge, which makes more sense if this is not just one triangle, but then there are different triangles where we all do these subdivisions. And in case of the immediate snapshot, it's actually not just a triangle, but the complete octahedron, and we do the subdivision of the octahedron. But this is much harder in TICS. Okay, so what can you do? Well, if you really think about knowledge and change of knowledge, you can determine that these structures of simplicial complexes and epistemic models are really one-to-one. You can determine a complete axiomatization for this system, which is the well-known logic of S5, plus one additional axiom that says that every agent knows its own values. And you can do other things such as define bisimulation, show NSC-Milner property, bisimulation correspondence, then model all kinds of distributed computing phenomena as action models, immediate snapshot, binary consensus, equality negation, and even you can conceive of novel epistemic features like define something that one might call common distributed knowledge. Actually, this term goes back to Alexandre Balta, as I recall, but Jeremy really liked this too. So this is, well, part of these results were in the PhD thesis of Jérémy Ledan at École Polytechnique, who was actually under the supervision of Eric Goubault. And I got in touch with these guys by way of Sergio Reisbaum. And I was also in the PhD committee. I was the rapporteur for Jérémy, yeah, one of the two. We have also made some common works on these matters, such as the final one here. This is not yet all. There are other ways to model this dynamics that is going on in ongoing research by Diego Velázquez and Armando Castañeda and David Rosenblut. These are all from UNAM in Mexico, and Diego is one of my extramuros PhD students, and Armando and David are his UNAM supervisors. Yeah. Something else you can do, but I will not talk about this very long because time is progressing. If you want to model not merely asynchronous computation, but also the interaction between synchronous and asynchronous computation, where it may be that processes crash or die, then you have simplicial, then this corresponds in combinatorial topology to simplicial complexes where the maximum dimension of facets is not unique. And this is an example. Here we have a simplicial complex with one triangle, dimension 2, and with lots of edges, dimension 1. So this models uncertainty over whether a process has crashed, which would be the case here, or whether it has not crashed, which is still the case here. On such a system, you can again consider defining a logic of knowledge, and this is what I've done in recent work called Wanted, Dead or Alive. I'd like to choose titles that are catchy. And then you can say things like, okay, we have here an impure simplicial complex. Consider the perspective of agent A. Agent A is uncertain between one-dimensional edge X and two-dimensional triangle Y. So what does A know? Well, A knows that as long as there is still an agent C alive, like here, that the value of that agent C is that 1 for the proposition 1C. So in a certain sense, you could say that in this system, agent A knows that the value of C is 1. And well, this we see described here, and then I can give lots of more explanations, but that I will not do here. And then you can ask yourself again the question, what is the complete axiomatization for this language interpreted on the class of impure simplicial complexes? And this is what is being described in this document, where it is again almost the logic of knowledge, but not quite. There are some defects, such as you cannot reason under the scope of knowledge. Okay, thank you very much.
So, good afternoon, everyone. I'm going to talk about expressivity of some versions of arbitrary public announcement logic. And this is a joint work with Hans-Van Ditmarsch and Mo Liu. This is me. Louis Couillard, this is my co-supervisor, and Igor Sadler. Okay, I will introduce some versions of arbitrary public announcement at first, and then I will give the definition of syntax and the semantics of them. And the main purpose is to show the expressivity of them. At the beginning, I will introduce public announcement logic and arbitrary public announcement logic again. And so public announcement logic has a dynamic operator represents the consequences of information change. So, for example, it can express after truthful public announcement of psi, phi is true, and it's known as, it has been shown that public announcement logic is as expressive as epistemic logic. And arbitrary public announcement logic, we call it APAL. It as a quantifier over PAL formulas so that it can express after any truthful public announcement phi is true. And it has been shown that APAL is more expressive than PAL. And APAL is undecidable of satisfiability problem, and it has an infinitary axiomatization. Now we will introduce some new versions of APAL. The first one I introduce here is called the subset version of APAL. We call it SAPAL. It quantifies over public announcements only containing a subset of items. For example, it can express after any announcement only containing items in Q, then phi is true. And the second version is called finite subset version of APAL. So as the example given before, if this Q is finite, we can say that after any public announcement only containing a finite subset of items, phi is true. So the third version is called the scope version of APAL. It quantifies over announcement only containing items occurring in the formulas within the scope of the quantifier. So for example, phi is the only formula within the scope of this quantifier. So this formula says after any announcement such that it contains only the items occurring in phi is true. And so a motivation of these versions of APAL is that when we deal with some independent subtasks, we may need some different vocabularies, so we need these versions of APAL. And the fourth version is called implied version of APAL. We may call it IPAL. So there are two kinds of quantifiers. The first one quantifies over announcement implying a given formula. For example, it can say after any announcement implying psi is true. And the second kind quantifiers quantify over announcement implied by a given formula. For example, we can see after any announcement implied by psi is true. And as we know that quantified announcement must be quantifier free, but for this psi as a parameter here, it may contain quantifier. So if psi contains quantifier, we have a quantified IPAL, we call it QIPAL. If psi is also quantifier free, then we have IPAL. A motivation of this IPAL is that formulas like after any announcement implying psi is true corresponds to substructural implication that psi implies phi. Okay, now I will introduce the definition of syntax and the semantics of these logics. First of all, for language of PAL, we see there is a public announcement such that after phi, and for the language of APAL, it adds a quantifier to the language of PAL. And for language of SAPAL and FSAPAL, there is a subset of atoms as the parameter to the quantifier. And if this subset is finite, then we have the long range of F as APAL. And for SC APAL, the scope version of APAL, the quantifier has a symbol of subset to show that this is a subset of the atoms. Okay, and for the language of QAPAL and IPAL, the quantifier has the formula phi and the down arrow and up arrow as parameters, and if this psi, I mean within this quantifier, this psi is quantifier free, then it is IPAL. Okay, here is the semantics. The semantics for the public announcement is defined as euro. We can see the definition of the update model is as euro. But for all these quantifiers, we can see it all quantifies over PAL formulas, which means it has no quantifier. And for these new versions of quantifiers, each adds a new condition to the original one, like it must be within a certain subset of atoms, or it is implying chi. It is the formulas implying chi or implied by chi. And to be more precise, here phi implies chi means that phi implies chi is valid. And psi is implied by chi also means that chi implies psi is valid. This is with the condition of the semantics of this quantifier of IPAL. Okay, now we are going to show the some results of expressivity of these new versions of APAL. First of all, for comparing of expressivity between logics, we introduce some notations. We see that a logic L prime is at least as expressive as a logic L if and only if for any L formula phi there is a L prime formula phi prime such that phi is equivalent to phi prime. And in this way, we can also define L is less expressive than L prime, and L and L prime are incomparable in expressivity. And here are their notations. Okay. So I will introduce a proof strategy in our paper, which I used multiple times to show that a logic L prime is not at least as expressive than a logic L. So suppose phi is an L formula, and therefore there are two classes of pointed models such that phi is true on every model in one class, but it is false on every model in the other class. Then suppose there is a corresponding L prime formula psi, and its model depth is n, and it only uses finite atoms within a subset Q. We can show that there is a pair of models for each class, such that these models are model equivalent with respect to L prime formula up to model depth n, or restricted to the set Q. And as psi cannot be true on one model and false on the other, there is a contradiction, so that we show L prime is not at least as expressive as L. Okay. So here we will give two examples of how we show this expressivity results. The first one, we could show F as APAL is not at least as expressive as APAL. So according to the strategy we talked before, here is a APAL formula, and here are two models. Model M has two states, 1 and 0, and the model N has 4 states, and its valuation and relations is depicted in the picture. We can show there is a APAL formula, which is there is an announcement after which KAP and not KBKAP. This APAL formula is true on the pointed state N10. This is because after announcement P or Q, the update model are like this, and this formula KAP and not KBKAP is true on this formula, so that this APAL formula is true on N10. However, this APAL formula cannot be true on M1. This is because KAP and not KBKAP is false either on this formula or the singleton M1. So this APAL formula is false on M1. So this formula can differentiate M1 and N10. On the other hand, we can show if there is a corresponding FS-APAL formula per se, and we assume that Q is a new atom, which doesn't occur in per se. So we can show per se cannot differentiate M1 and N10. This is because actually M1 and N10 is bisimilar without the atom Q. And if per se has no atom Q, then it is true on M1 if and only if it's true on N10. So by this way, we show that there is one formula, one APAL formula, which any FS-APAL formula cannot express. And the second example here is APAL is not at least as expressive as FS-APAL. So the strategy is same. We have two classes of models, and we have an FS-APAL formula, and this FS-APAL formula is true on all models in one class and is false on the other one. This is because now we introduce these two classes of models. The first one we call MN, and the second one we call NN. They are both AB chains, which means they are a circle, but the relation between them is BA, 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 and the length of MN and NN is both 2n. It's from 0 to 2n minus 1, so there are 2n states on each models. Okay, and we can show that there is a one FS-APAL formula which after any announcement only containing atom Q, then not Q and KAP and not KBKAP. This formula is true on MN0 and it is false on NN0. This is because for the valuation on MN, P is true on the even states and Q is true only on N. And on the NN, the valuation is the same, but only R, atom R, is true on the state NNN. Okay. So by the character of the AB chain, we can say every state is definable by a formula only containing atom Q. This is because MNN is defined by Q, and each other state can be defined by the distance is from Q. Similarly, each state on NN can be defined by a formula only containing atom R. So after announcement only containing Q, we can have an update model which only has states 1 and 0, and this formula not Q and KAP and not KBKAP is true on this updated subformula MN0. So on the other hand, on NN, it cannot be done by a formula which only containing atom R. So this FS-APAL formula cannot be true on the NN0. And now we suppose per se is a corresponding APAL formula to this FS-APAL formula, and its model depth is n. now we can show that this APAL formula per psi cannot be true at Mn and be false on Nn0. This is because we can show that Mn0 and Nn0 are n bisimilar. However, we know that n bisimilar doesn't imply that they are model equivalent in general for all APAL formula, but it can be shown these results on these particular classes of models Mn0 and Nn0. The tricky part is that every subset of MNN and NNN are also definable by Q or R and P, so that if there is a subformula of MNN, we can find a corresponding formula such that the corresponding subformula of NN also can be definable. In this way, we can make an induction on all APAL formula such that we show that this per psi is true on Nn0 if and only if per psi is true on Nn0. So therefore, we can show that APAL is not at least as expressible as FS-APAL. And now, due to the limited time, we only give a brief introduce of other results. We can also show that FS-APAL is as least as SS-APAL. This is because we can just list the atoms occur in phi. On the other hand, SC-APAL is not at least as FS-APAL. This means SC-APAL has strictly more expressible than FS-APAL. And for APAL and APAL, we can show that APAL is also strictly more expressive than APAL. So the proof, detailed proof are omitted here. And we can also show that APAL are incomparable with respect to FS-APAL and SC-APAL. So give a conclusion here, we can draw a picture we call expressivity hierarchy of logics presented in this work. So in this picture, an arrow means that larger expressivity, and we assume that this arrow is transitive. And if there is no arrow between two logics, that means they are incomparable. So as we can see, FS-APAL is strictly more expressive than SC-APAL, and SC-APAL is also strictly more expressive than PAL or EL. On this branch, IPAL is strictly more expressive than APAL. And meanwhile, both FS-APAL and SC-APAL are in comparative of expressivity with IPAL or APAL. Here is the main result in this project. Okay, here we go to the conclusion. So in this project, we investigated the expressivity of FS-APAL, SC-APAL, and IPAL. And on the other, what's more, we expect those logics still to have undecidability of satisfiability problem and infinitary exclamation. This is similar to APAL. And we also investigated the IPAL quantification provides a refreshing perspective on dynamic consequences motivated by substructural implication. This is something that I have no time to introduce here. Okay, thank you.
Thank you. Maybe there are any questions to the final presentation?
Oh, I have no particular question, just to say that it was a nice talk.
Thank you.